Exploring Life Chapter 2, Fundamentals of Atoms. Part 1. Every story has a beginning, and the story of life begins with the universe. To understand ourselves, we first need to look at the cosmos that gave us birth. Did the universe have a beginning? The leading explanation is the Big Bang, the moment when space, time, matter, and energy all came into existence, starting the universe we can observe today. According to the Big Bang theory, the universe began about 13.8 billion years ago as a singularity, an unimaginably small, hot, and dense point packed with pure energy. In a tiny fraction of a second, this energy expanded rapidly, giving rise to space, time, and matter. That explosive moment marked the beginning of the universe as we know it. How was matter generated from energy? Einstein's famous equation, E equals mc squared, tells us that energy and mass are interchangeable, each can be transformed into the other. In the earliest moments after the Big Bang, the universe was pure energy. As it expanded and cooled, that energy condensed into particles of matter. Later those particles combined to form the first atoms. It took hundreds of thousands of years for particles to join into the first atoms, the building blocks of stars, galaxies, planets, and everything we see today. Billions more years passed before complex molecules emerged. And here's the fascinating part: the universe is still expanding, even as you listen to this lecture. Hydrogen is the oldest and most abundant element in the universe. It's also the simplest, just one proton and one electron. Hydrogen makes up about 75% of all normal matter by mass, and over 90% by number of atoms. Over time, tiny ripples in density let gravity pull this gas into immense clouds, where the first stars ignited. In their cores, hydrogen fused into helium, releasing enormous energy and lighting up the universe. Helium, the second most abundant element, now makes up nearly 25% of the cosmos. Together, hydrogen and helium laid the foundation for every heavier element, and eventually, for life itself. But hydrogen and helium were only the beginning. Inside stars, nuclear fusion forged elements up to iron. Heavier ones, like gold and uranium, were born in a different way, during supernova explosions, through neutron capture reactions. A supernova is the violent death of a massive star. In those final moments, powerful blasts scatter newly created elements across space, seeding the raw materials for future stars, planets, and life. Every chemical element around us, and within us, was forged in the hearts of stars and in the violence of their deaths. This dusty donut is one of hundreds of billions of galaxies in the universe. It's catalogued as NGC 4526, about 55 million light-years away in the constellation Virgo. The bright spot on the lower left shows a supernova, SN 1994D, exploding inside this galaxy. In that instant, it scattered newly forged elements across space, enriching the cosmos and paving the way for future stars, planets, and life. In everyday life, objects stay put and time flows steadily. This is classical physics. At cosmic scales, gravity bends space and time. Near a black hole, it can nearly stop time itself. At the tiniest scales, quantum physics defies logic. Particles exist in overlapping states, in many places at once. And yet, Our modern electronics work precisely because quantum physics is real. Classical physics, quantum physics, and relativity are like different harmonies, each beautiful on its own, yet not blending into a single song. The search for a theory of everything is really a search for the full symphony. String theory imagines tiny vibrating strings, each like a note, creating particles and forces. The universe is a grand symphony, with life as one small melody. For now, it's more philosophy than science, so we return to the tangible world, where atoms, energy, and evolution shape everything we are. The Big Bang is the most widely accepted explanation for the origin of the universe, but it's not the only one scientists have considered. Exploring other ideas helps us test the limits of what we know. Question for you: what other theories have you heard about? Some possibilities include the multiverse theory. Our universe might be one of many. The oscillating universe. The cosmos could go through endless cycles of expansion and collapse. Share any ideas you've come across from science, documentaries, or even science fiction. Which do you find most interesting, and why? From galaxies to particles, physics seeks unity. But in the realm we can directly measure and touch, reality appears as matter. So let's zoom in from the search for ultimate theories to the concrete question: what is matter made of? Matter is anything that takes up space and has mass. It includes everything we see, touch, and even things we can't see, like air. At the most fundamental level, matter is built from fundamental particles, quarks, leptons, bosons, and a few others. These combine to form subatomic particles, which then come together to create atoms, the foundation of everything in the universe, from stars and planets to people. Here's a table of the subatomic particles: protons, neutrons, and electrons. Their masses are measured in atomic mass units, AMU, with 1 AMU defined as about the mass of a proton or neutron. These particles also differ in electric charge. Together, they form atoms, the fundamental building blocks of all matter. Now let's see how these particles are arranged inside an atom. Protons and neutrons sit tightly packed in the nucleus at the center, while electrons move around the nucleus in regions called electron clouds. This basic structure gives each atom its identity and allows atoms to interact and build everything around us. To give you a sense of scale, if the nucleus were the size of a ball, the electron would be like a tiny fly buzzing several hundred yards away. So the next time someone jokes that life is empty, scientifically speaking, they're absolutely right. An atom is the smallest unit of matter that still retains the chemical properties of an element. For example, a single hydrogen atom is the smallest possible amount of hydrogen that can still behave like hydrogen. Atoms are incredibly tiny, so small that about 500 quintillion could fit into the volume of a single period at the end of a sentence. A quintillion is a 1 followed by 18 zeros. Try to write it down, it'll take a minute, right? There are two common ways to illustrate atomic structure, shown here using helium as an example. The planetary model shows the nucleus at the center with electrons in fixed circular orbits, like planets around the Sun. While this is an oversimplification, it's useful for visualizing the basic layout. The orbital model, on the other hand, represents electrons as a cloud surrounding the nucleus. This depiction is more accurate and is especially helpful for predicting how atoms behave during chemical reactions. Both models remain valuable tools for illustrating chemical structure and behavior, each serving a different purpose in understanding the atom. The atomic number of an element is the number of protons in its nucleus, and it's what defines the element. Each element is also represented by a unique 1 or 2-letter symbol, like H for hydrogen or O for oxygen. These symbols are used on the periodic table and in chemical formulas. Because each element has a different number of protons, they also have distinct chemical properties that determine how they interact with other elements. Atomic mass, also called the mass number, is calculated by adding the number of protons and neutrons in an atom. Technically, electrons also have mass, but it's so tiny compared to protons and neutrons. Protons contribute a positive charge to the nucleus, while electrons, with their negative charge, move around the nucleus in an electron cloud. In a neutral atom, the number of electrons balances the number of protons, making the overall charge 0. Electrons aren't scattered randomly. They're arranged in layers called electron shells around the nucleus. An atom can have up to 7 shells, and each shell holds only a certain number of electrons. The first shell holds just 2 electrons, the second can hold up to 8, and the third holds up to 8 in simpler atoms, with larger atoms holding more in higher shells. Electrons always fill the closest shell first before moving outward. You can use a simple analogy. Think of it like arranging seats, 2 chairs in the first row, 8 in the second and third. Just like students at a graduation, electrons fill the front row before moving to the back. The electrons in the outermost shell are called valence electrons. These social electrons decide how an atom bonds, reacts, and interacts with its neighbors. A chemical element is a pure substance that cannot be broken down into simpler substances by chemical means. Each element is made up of atoms with the same number of protons in their nuclei, and that proton number is what defines the element. So whether it's a single atom or a chunk of metal, if the number protons match, it's the same element. Now that you understand what elements are and how atomic number defines them, it's time to see how all that information is organized. Get ready, because in the next part of the lecture, we'll explore the periodic table, the ultimate cheat sheet for chemistry, biology, and beyond.